Another line of research in association rule is actually to consider multidimensional rules. So if we talk about just simple items, we could express the rule as bread implies butter. But if you want to put that into another formalism, so we have bread implies butter, that actually we could write also similarly with a different syntax as buy X bread implies buy X butter. So where X is the customer. Customer who tend to buy bread tend also to buy butter. So if we move toward a multidimensional rules in which we talk about maybe the age of the customers, then we could include what we call more predicates. In this case, we could express a rule like if X buys pizza and age of X is young, which is a young customers, then X is likely to buy also Coke. So we are going to just extend the framework by using what we call predicates. We would include variables, and this will allow more expressiveness in the formulation of the rules. So in this case, instead of talking about items, we talk about predicates. Instead of talking about K item sets, we talk about K predicate sets. So another question is, how about how do we handle numerical features or numerical variables in the case of association rules? So we could simply think about what we call discretizing or splitting the domain into different intervals. If you want to be specific about how young are the customers, you could say that most of the people who buy pizza who are between the age of 18 and 22 tend also to buy Coke. So I'm going to discretize the feature of age by in different ranges. But we will see that this is not necessarily the best approach to handle numerical features in the case of association rules. Another fact about association rules is that they may lead to a very large number of rules, which makes it difficult to sift through the rule to find the nuggets or the interesting relationships. So how can one reduce the number of rules? This can be done in different ways. We could use many evaluation measures. So I've seen that we have the pair support confidence. We could make it as a triplet, support confidence interest. We could use also there are other evaluation measures that were proposed in the literature. What we can do also is to increase the minimum support. The more you increase the minimum support, the less frequent patterns you generate and the less rule you will generate. We could also increase the minimum confidence, which means that we are really interested in very strong associations that are, let's say, confident by 80 or 90%. Finally, we could impose some rule templates, in which case we are not going to generate all possible combinations of items on the left-hand side and the right-hand side of the rule, but we are going to just maybe focus on one item on the left-hand side, one item on the right-hand side, and even be specific about what features to use, etc. So which means that defining constraints on the length of the rule, on the items to put in, and to include some specific items or exclude some of them. Okay. I wanted to talk a little bit now about the implementation. There have been very successful implementations of mining association rules. There is actually a repository of algorithms and data set that you could explore. It's called the FIMI, Frequent Item Sets in Mining Implementations Repository, that actually is maintained since 2003. There have been, after 2 workshops called FIMI 03 and FIMI 04. So this website here will give you a wealth of information about data sets and algorithms that are implemented that you could use and try. There is also a famous implementation by Borgelt of the a priori algorithm and some of its variants that you could find in this link here. You probably know the system Weka, which implements many data mining algorithms and machine learning algorithms, and includes actually a strong module on mining association rules. And finally, there are many others, and if you're interested in using MATLAB for mining association rules, there is the system Armada that you could explore. And there are many, many others, but these are the ones that I think are the most well known. There have been also several extensions of the a priori algorithm since the seminal work from Agrawal. Actually, the different algorithms are based on different search strategies, which you know well now. Breadth-first search has been the first approach in which the algorithm goes level-wise in the lattice, level by level. And this is actually very time-consuming when the size of the frequent item set is long, which means that we have to go very far in the lattice breadth first search. Methods doing breadth first search include the a priori algorithm itself, some extensions of it to use transaction identifier intersections, partition, DIC, etc. Methods that use depth first search include ECLA, click, and depth project. And finally, there were some methods that combine the benefits of depth first search and breadth first search, such as a priori hybrid, Viper, and DCI. Other methods are actually using a graph representation of the data and finding patterns on those. And these methods are called pattern growth. This means that there is no candidate generations, but the data is represented in graph. Methods like this include FP growth, HMINE, Coffee, etc. So this has been for some time really an active research area to find the best way to address the computational complexity of the problem. So you have seen so far that we are talking about a transaction data set in which we have the examples in lines are sets of items. The framework has been extended to the problem in which we have a simple machine learning table in which we have the examples in the rows and we have the features in the column. So a priori has been initially designed for what we call Boolean tables or transaction databases. So in this case, propositional logic has been sufficient to express the items, the item sets, and the rules, such as milk implies cereals. In the case where we have a regular table, like in the machine learning original framework, in which we have rows and columns of features, we're going to talk about relational tables, and we can extend the framework and the notions of items and to literals. So in this case, an item is no longer an item in the table, like an item in a supermarket, but it's a pair of attribute values, such as age, 20, and this attribute value is seen now as an item to generate frequent item sets. In this case, an attribute could be seen as in three categories. The first one is categorical. This is simply cereals, color blue, etc. It could be quantitative with actually a few numerical values. For example, number of cars could be either 1 or 2. It's rarely that a family has 3 or more cars. So it's more like a numerical value with a few numericals. For example, number of cars 2 could be a pair attribute value and could be seen as an item. And finally, if the quantitative or numerical value has large domains, then we have to discretize, and in this case, the item attribute value would be something like age in the interval 2040. So we build items depending on the category of attribute that we have, either categorical, quantitative with few numerical values, or with large numerical values. So here's an example inspired from the literature. Suppose we have a data set of people, D. This data set has actually a set of examples. These are our examples, just like in regular machine learning framework. We have the transaction identifier or the line identifier. This is the first example that has an age of 23, who is not married and who has 1 car in the family. So we are going to have this table, which is a table without a label, so there is no label. It's completely unsupervised. And we are going to example of extracting a frequent item sets, in this case, predicate set, would be the age in the range 2029, the age in the range 3029, whether the person is married, yes or no, the number of cars 1, number of cars 2, and combine this kind of item sets, such as age is in 3039 and married is yes. So we're going to calculate the support in this table. For example, this last item set is actually frequent in 2 of the examples. There are 2 examples with age between 30 and 39 and who are married. These are these 2 lines here. We're going to apply the framework exactly similarly, but this case the item is just has a different formulation. And from this frequent item set, we are going to generate the rules, such as this one that expresses that basically 66.6% of people aged between 20 and 29 has only 1 car. And this rule, which means that number of people in this age range and with this number of cars actually represents 60% of the table here. So we're just reformulating the problem in this case where we have a more complex kind of items in the data set.